Hey everybody, Mr. Gibson here. So for this assignment, this is Explain 1.3, and it's another assignment that I've given you 2 days to do because this can be a rather large assignment because it's got two big steps. You're going to fill in your interactive notes like you've done before, and then you're going to do the summary page, and hopefully you'll watch this video to get help on the summary page and make sure you have the correct answers. So let's just read the instructions. It says, I'm giving you 2 days to complete this assignment. Open the PDF with Kami. Using the information from the Google Slides, fill out the blanks. Remember, the questions on the side are there to help you study. You don't have to fill them out right now, but when you're studying for your quiz, which right now is scheduled for Monday, and what date is that? That is the 21st. So you've got that coming up. Once you're done with that and you've filled out the summary overview pages, then you're going to finish this video. So if you haven't done that yet, stop this video, go do that, and then come back and watch the rest of the video of me going over the summary pages. All right, and remember at the very, very end of this to click on the link or to go up, hit share, copy the link, and then put that link into your interactive notebook, and that'll be a part of your notebook grade. So let's take a look at this PDF here. And so what this is walking you through today is the different models of the atom over time. And what I mean by that is different ways that people have thought of the atom or thought the atom looked like over time. It's going to start in ancient Greece and walk you all the way up through modern day. Okay, now what I want to do real fast is show you how to share this document. So you are going to click share, and then here's your link. So you'll just take this link and you're going to put it, copy and paste it into your interactive notebook, probably on a slide labeled something like Unit 1.3 Interactive Notes or something like that. Okay, so hopefully at this point you have filled this out. You filled this out. There's quite a bit to fill out here, so I'm giving you 2 days to do it. John Dalton had 5 parts of his the principles of his theory. So yeah, quite a bit to fill out there. And then walking us all the way up through our current understanding of the atom, which is the quantum mechanical model, which was formulated by Erwin Schrödinger. And there's his very happy looking picture right there. Okay, so here's the summary pages, and let's just not waste any more time and just go through these as fast as we can. I will move kind of fast because where this is a video, if you're like, oh, he went too fast on that, I need to go back and watch it again, you can. Okay, you can go back and watch any clip of this that you need to. Let's use purple this time. I like purple. All right, so it says, who was the first person to come up with the idea of the atom? Well, this was Democritus, and this was in ancient Greece, like 400 BC, so a long time ago. And according to him, everything in the universe was made up of 2 things: atoms and empty, whoops, I'll do an atom there. He thought it was made up of atoms, and whatever was not made up of atoms was made up of empty space. So he's pretty close. We do have some exceptions to that, but that's like quantum physics that we won't get into. So for someone who is not a scientist and just a philosopher, he reasoned his way to a pretty decent understanding of the universe. Now, was his model of the atom super accurate? No, but the fact that he originally came up with the idea of the atom is a pretty big deal. So what are the 2 basic reasons that this model died out? Okay, so his model didn't last very long. The Greeks didn't really pick up on this and run with it. Well, one main reason is he could not explain chemical behavior. He didn't have an understanding of chemistry. There wasn't chemistry back then. There was alchemy, which was like a mix of chemistry and a little bit of magic, I guess. So he didn't have a science background. He was a philosopher, so he couldn't explain the chemical behavior of different substances. He also, his model did not have scientific support because you weren't able to have scientific support back then. They didn't have electron microscopes where you could go in and look at individual atoms. Okay, so This was his theory, and this is why it kind of died out. Now, it died out and stayed dead for a really long time, all the way up until the early 1800s. And the idea of the atom was brought back by John Dalton, who was actually a school teacher. And what year did that happen? Well, it was 1803, so still quite a long time ago by our standards, but in the standards of like all of human history, relatively recently. So what two chemical laws did Dalton use to help build this model? So he figured this out using the law of conservation of mass, one thing, which states that mass or matter cannot be created or destroyed. And he also used the law of definite proportions. All right, those are the two laws that helped him build his model. And his model had 5 principles, and I'm just going to state those really quickly. The first part of his model was that all elements are composed of atoms. Pretty solid so far, right? Second part of his theory, his model, was that atoms of an element are identical in size, mass, and other properties. So, and are different from atoms of other elements. Okay, I'm going to do my best to fit that on there. I'm just gonna make it. Yeah. So, I have an idea. I'll do this. So atoms of one element are identical in size, mass, and other properties, and they are different from atoms of other elements. Now that's pretty close. Now you guys know about isotopes, where atoms of one element can have different masses because they've got different numbers of neutrons, but he had no idea that subatomic particles even existed. So you guys actually have a leg up on John Dalton right now with your knowledge. So, but that was the second part of his theory, and the third part was that atoms cannot be created, destroyed, or divided. Now, we now know that to be false because, again, you guys know about the subatomic particles. Atoms, they're actually things smaller than atoms. There's protons, electrons, and neutrons. So it can be divided. He didn't know that back then, though. And atoms of different elements can combine in simple whole number ratios to form chemical compounds. That is also true. That's kind of the foundation for chemistry there. You'll learn more about that later in the class. And finally, in chemical reactions, atoms are separated, combined, and rearranged. And that is also true. All right, so was his theory good? It was okay. His model was okay, but it wasn't fantastic because he still had some things wrong. What's another name for his model? Well, his model, if you remember, was the atom was just a sphere. And I don't know if anyone has ever played pool, but he called it the billiard ball model. In pool, you play with billiard balls, which are just smooth round spheres, and that's what he thought atoms look like. Okay, so what fundamental chemical law did Dalton develop based on this theory? He developed the law of multiple proportions, and this is going a little bit deeper than what you will need for the test, but that's okay. Nothing wrong with learning a little bit extra. And the law of multiple proportions just states that when elements combine in more, and I'm going to jump down here. than one proportion to form two or more compounds, the weights are of the elements are in small whole number ratios. I'm having to do a little Cami magic to get these to fit, and you can do that too. Okay, so he came up with law of multiple proportions, which says when elements combine in more than one proportion to form two different compounds, the weights of the elements are in small whole number proportions. And that's something, it's a little deeper than what you need right now, but it's something that will make sense later on in the class. So what is the first model to replace Dalton's atomic theory? Because remember, his theory isn't great. It's not super solid. He thought that atoms were the smallest thing ever. You couldn't divide them anymore. We know that's not true. So the first model to replace his was made when J.J. Thomson discovered the electron, something smaller than an atom, and J.J. Thomson came up with the plum pudding model. So the first one to replace that was the plum pudding model, again developed by J.J. Thomson, because he discovered the electron. So if you remember what the plum pudding model looked like, it's down here. It was a sphere of positive charge with small negative charges, which were electrons, spread throughout. Okay, so, and you saw a model of that, you saw a picture of that. So the plum pudding model, he said this, he didn't know what protons were, so Thomson said, no, atoms are divisible. Dalton's wrong, but instead of just a sphere that's indivisible, it's a sphere that has a positive charge with a bunch of little negative charges inside of it called electrons. Now, someone conducted an experiment using the gold foil experiment. Hopefully you remember who that is. And he found out that the atom has a nucleus, and he called his model the nuclear model, and that was Rutherford. Remember Rutherford's gold foil experiment. He was the first to propose the nuclear model, or a model with a nucleus. Okay, and he had two predictions that he put into this model, that atoms have a massive atomic center. So there's some sort of center in the atom that holds a lot of mass, called the nucleus. And he also said that the electrons revolve around the nucleus. So he was pretty close to a good, accurate model of the atom, a lot closer than the plum pudding or Dalton's model. Now, the only issue is he couldn't explain the behavior of those electrons, specifically how they revolve, and he didn't know what the particles were in the nucleus. So who confirmed the nuclear model of the atom? Actually, sorry, I misspoke. That was not Rutherford. Rutherford was the first one to confirm it. The first person to propose it without testing it was this dude here. My bad. Agaoka. Okay, so what experiment was used? That was the gold foil experiment. You guys actually did a simulation where you recreated that experiment, which is pretty cool. So according to classical physics, what will happen to electrons in the nuclear model of the atom? So if you have some light particle that's orbiting something that has a really big mass, what eventually would happen? Well, eventually they would spiral closer and closer and collide with the nucleus, according to traditional physics. So the electrons would lose energy and collide with the nucleus. Now, we know that doesn't happen, because you're not walking around down the street one day and all of your electrons just collide with the nuclei and the atoms in your body and you just blink out of existence, okay? So, so we know that Rutherford's model couldn't 100% be true, because he couldn't explain why the electrons weren't just colliding with the nuclei. So instead, when electrons give off energy, they're not going to collide with the nucleus. So what do they do instead? What happens when atoms give off energy? Well, this is something we're going to talk about a little bit more in 1.4, but they give off light at very specific frequencies. And you guys, I don't know why I did that. Give off light at specific frequencies. You want to see this happen? Go turn on the lights in your room right now, because that's exactly what causes all light around us is this process here, atoms giving off energy because of their electrons. So let's just recap. We've got Democritus, then Dalton's model, which is just the billiard ball model. Then we had J.J. Thomson's plum pudding model. Now we have Rutherford's nuclear model. We're going to move on now to the Bohr planetary model of the atom. And according to Bohr, the electrons are found in orbits around the nucleus. Okay, and what do we call those fixed orbits? We call them energy levels. And this is the model you're used to using because it does a pretty good job at explaining how atoms work, but is also fairly simple and easy to draw. So you've got the nucleus, and you've got the first energy level that holds 2 electrons, the second that holds 8, the third that holds 8, and you guys can use that to find valence electrons, all that stuff. This is the model you're used to seeing, okay? So let's keep going. True or false, electrons can have all possible energies in the Bohr model. That is false. Electrons have fixed energies. They have specific energies. They're found in certain energy levels. They can't just fly all around anywhere they want to. So what do we call the amount of energy needed to move one electron to another energy level? Well, we call that a quantum. It takes one quantum to move an electron to a different energy level. Okay? So what model was developed to better explain the arrangement of electrons in the atom to replace the Bohr model? So we've had Democritus, Dalton, the plum pudding model by Thomson, Rutherford's nuclear model, the Bohr model, which is the one we like to use because it's easy, but it's actually not the most accurate, at least not based on our current understanding. So there is a model that is the most accurate model of the atom, and that is the quantum mechanical model. Super fancy sounding. And this was developed by a guy named Erwin Schrödinger. Okay. So instead of electrons having nice circular orbits around the atom like we're used to seeing because it's so easy to visualize, instead electrons can be found in a cloud. We call it the electron cloud that surrounds the nucleus. So you can see a picture of it down here. Now, why do you think that cloud is there? Why is it more accurate to describe it as a cloud? Well, here's why. The electrons are moving so fast, all you see is a blur. Okay, we cannot use our finger and point out at any given time where an electron is. They're moving as fast as Barry Allen in The Flash. Okay, it's just a blur. So like propellers on a plane. So it's moving so fast, we just see this blurry region where we know the electrons are because we see the blurry region, but they're too fast to pinpoint at any given time. So he had to use equations to find the probability of where an electron would be within the electron cloud since we can't see it with our eyeballs. And we call those equations wave functions or wave equations. Okay? It's more math than I know how to do. So we're just going to leave it at that. It's very complicated math, the wave functions are. So another important guy who helped with the quantum mechanical model was Heisenberg. You may have heard of the Heisenberg uncertainty principle. And that's his contribution to the quantum mechanical model is the Heisenberg uncertainty principle. Basically, you cannot for sure be certain where an electron is. You just know it's in that blurry region. I hope that makes sense. That's a lot of information here. So let's just summarize it all with this. This will help you guys a lot on the test, so make sure you pay close attention to this. So this here kind of looks like a billiard ball. So we're going to call this the billiard ball model. So that's B right here. And who is that developed by? It was developed, if you remember, by John Dalton, which is 2 over here, II. So put that there. I would like to go in order of. So let's back up just a second. Who came before John Dalton? Well, if you remember, it was Democritus who came up with the original idea for the atom with his atomic model. Okay, so he just knew atoms existed. He didn't really know what they looked like. He knew that they were the building blocks of the universe. So we've got some building blocks down here. Now, we had Democritus, then Dalton, and then J.J. Thomson discovered the electron, disproving Dalton's model. So now we have the plum pudding model right here, which is the letter E. And again, that was developed by J.J. Thomson, or Roman numeral 6. Okay. After that, Rutherford discovered that there was a nucleus inside of an atom. And so that model was called the nuclear model, and it looked like this up here at number 26. Okay, and again was proposed by Rutherford. All right, after that, Bohr came up with the idea that electrons orbit the nucleus in fixed energy levels, and we called that the planetary model because it looked like the electrons look like planets orbiting the sun when they orbit the nucleus. And again, this was proposed by Niels Bohr, which is Roman numeral 4. And finally, we have our modern understanding of the atom, which if there's a new discovery, it could totally change tomorrow, but it's the one that science is running with right now. And this is called the quantum mechanical model, and this was proposed by Schrodinger, or Roman numeral 1. All right, guys, there you have it. There's a lot of information, so you may want to go back and watch this video again in chunks. But we've got our summary pages, and we've got a summary of all the models and who discovered them. Okay. If you need any more help, feel free to email me or call me. Make sure you use this to study for your next quiz. All right, guys. Good luck.